Homework? An exchange? It's like a kind of a team version. Wow. You must say so. Why do you think I was stupid? You always ask the roof steeper. All right. You ready? Homework? Not stable. All right. 4 or 5, right? Something like that. 7, 8, or 9. Are you really out there today? Yeah. Jim. Why? Someone stole a dry erase marker. You were doing really? No. Oh, I said marker, but I meant dry erase. Okay, so we have a conundrum. We have a problem. Okay, what's the problem? We're not talking about that. What's the problem?
There's another test coming up?
No. No. Let's remember, everyone watched the video for the last lecture. So you know exactly what the problem is, even if you weren't here.
Yeah.
Right. You don't want to be lost in class. Right? So what's the problem?
Were we still in the force?
Yeah, we're on the force.
To electrons?
Yeah, let's look at it again. Okay. Okay. I have an electron here. I have an electron here. So there's E1 plus E2. Names. Okay. First question here. What's the force, the electric force on 1 from 2? So the electric force from 1 on 2. Okay, is equal to just the we read the electric force.
Oh,
Q times E. Okay. So that means that I can look at this one. I can say that the electric field for E2 is going out radially. And so I can say, well, this is the direction of F1, 2. And for E2, what do we have? The opposite. Okay, so here, perfectly drawn, and this is F2, 1. So then I can say something very simply, and that is F1, 2 is equal and opposite F2, 1. As long as we're just talking about the electric force. Okay, so now I'm going to treat them as though they're moving. And this one has V1. This one has V2. Okay. So now I can imagine that they will create what type of field? Magnetic fields. And those have the form V cross B. Okay, and specifically, if we want to look at this one, this is the force on one from two. 1, 2. Right? Okay, so let's work this out. So what is the force of E cross B? This one? Sorry, V cross B for this one. So V1 is going in this direction. And where's the V field? Which direction is it in? This one's going in, following particle 2. It's coming out of the board, right? Good. So here, B2 is out of the board at us. And this one here, where's B1? Into the board. Let's see if I can follow that. Into the board. Very good. All right. So now we do our cross product. B. I'm gonna do cross one. B. Oh, okay, good.
What? What's it about?
Yeah. You tell me, I don't know. Is it?
I had to reteach myself this, and I was like 1, 2, and then so.
Yeah.
Okay, so show me again. So you're pointing 1, and then you're using this finger as 2.
The second thing and then the.
Awesome. All right, so now we're all on the same page. So this is now F, B, 1, 2. And of course, we know that the forces should be equal and opposite according to Newton's third law. So then we just say, oh, well, this one must be straight down, right? Oh, you don't think so? So you're either telling me that Newton's third law is incorrect. It's too old. Some new stuff came out since then. You haven't seen Newton the remix. All right. So what's this one then? Let's do the shape. Okay, so
Oh, wait, sorry.
This way.
show me your hands. One hand at a time. Someone just give me one hand. You have to do it in the order. I can't see it. One,
You.
One. dude, that one?
Yeah,
One,
so.
2, 3.
Alright, 6. So this one's this way? F, B, 2, 1.
Yeah.
Everyone happy? No. You should feel uncomfortable, not just because it's cold in here. It's not cold in here.
I wish I rolled it again.
Okay, so you have one that's going this way, you have one that's going that way.
So you get like a.
So I can say that FB, comma 2, 1 is not equal and opposite to FB 1, 2. Newton's laws
So,
broken forever. Death to happiness. Right? All right, let's go.
Don't they have the same magnitude?
Okay, good. So they made up the same magnitude, but the directionality is screwy. Yeah.
Is it because they're moving? Newton dealt with like non-moving stuff.
Well, Newton, remember, cut his teeth. He learned everything about the world. He learned everything about the world based on the movement of planets.
yeah.
Okay. So is this true?
Yeah.
No. This is called a
Paradox.
paradox. And what are paradoxes? What's a paradox? You can't explain it because
You don't know yet.
you don't know enough yet. So paradoxes are always resolvable because you just simply don't know the math. You don't know what's going on, right? So here we're thinking to ourselves, well, I only have 2 forces here, so equal and opposite, everything's broken. No. We showed earlier that E and B fields can carry with them energy. What was that called? Fun name, something we do sometimes. Pointing. Okay, so we saw that S, which is defined as the right pointing vector. And what did that do? That's how you make it, but what does it do?
Field does work on charge creates field.
Ah, does work. So this thing can communicate energy. So E energy from fields E and V. That's supposed to be an ampersand. I'm not gonna do that better. Okay. So now we're gonna learn more things. Because I'm going to tell you that fields can also communicate momentum. And if fields can communicate momentum, then they are able to transport forces. Just as a quick aside, if you remember from your classical dynamics, how do we write forces in terms of momentum? Right. So I could say something along the lines of ddt of P. Now you are going to get very upset today, not just because I'm talking, but because we are going to use P's and P's. Okay? One of these P's is,
What is this?
don't start with me. That would be 3 P's. But we will get there. Momentum, good, the one that I just said. Okay, so we're gonna have to be careful. Okay, momentums are P.
Peak.
Peak for momentum. Okay, and what's this one? Power. Ultimate power. Okay. Momentum, okay? That makes sense? The P is silent. Cool. This gonna work?
Yeah.
Okay, no crying today. Well, at least not right now. Okay, so I'm gonna argue that the fields carry momentum, and in order to do that, we're going to have to dig deep into ourselves and remember fluids. No, I hated fluids. Don't do this to me. Okay, so let's start off. What does the full force look like again? Force per unit volume, perhaps. F is for both pieces.
What?
Yeah, let's just do forces. So the electromagnetic forces on a charge is good QE, you hear that? And what's that? Say it louder. V cross B. Okay. We like this. And we can do a fun thing here. We can distribute this over. Okay. And we could say something along the lines of QE plus QV cross B. And then I can say, well, what happens if I divide both sides by the volume? Then this thing is divided by the volume, and this thing is divided by the volume. And this is charge density. Notice the upturn, that's a rho. And this thing is? Nope. The current density. Because remember, I'm multiplying by V. So this has to be J. And then this one is silly, this is just little f. So generally speaking, when we see little letters, they mean the volume density of that. But if I'm using a little p, that means momentum. Okay? All right. So here's where we start. Okay? So this leads us very naturally. The little f is equal to rho E plus J cross B. That's how I communicate forces, right? Okay. Can I write this in terms of the fields?
They're right there. E and P.
Only. Field only. You're right that they are right there, but can I write them only in terms of the fields?
Like one instead of the other.
No, just like, I don't really like rows, no one can even understand if that's a P or not, you know, I just really wanna simplify it for y'all. Want to make it really easy to understand.
Yeah, go ahead.
You're good, you have infinite faith, how would I do it?
You're really representing to polarization.
I don't want, no, I only want E's and D's. You're right that we could certainly do something like that, but I only want E's and D's.
For row E, is this something with like Gauss's law?
Ah, interesting, so we could go back into our mind brains and find, say, Maxwell's laws?
Yeah.
Okay, so have a look at your notes really quickly and tell me how I get this one. And how I get this one.
Oh,
For row, it should,
Hold on, this one. Rho is
divergence of E,
divergence of E, that's it.
all times epsilon.
Good. Good, and then someone else for J. Yeah,
Del cross B minus that one not.
is that it?
There's
Okay, you're not for all of it, so let's make sure we don't miss that. Okay, so we're gonna start with something like 1 over mu naught. And then del cross B you liked. Okay, and then is that it? Minus or plus? Minus
Epsilon not.
epsilon naught.
And E.
And that's what you're happy with, right? No one's happy with this. Okay. So, yeah,
You did that just so you can get E's and B's and no rows and all that?
yeah, I want F just in terms of the fields. Because I wanna know whether or not the forces can be communicated with the fields and whether that tells us anything interesting about what we're doing. So specifically here, you can separate some E's and B's and you can use a lot of very fun notation here. But I'm gonna show you the answer and I'm gonna tell you how happy this is, okay? Super easy, everyone would have gotten this directly in their head, right? Only 1/2 of it. Okay, super straightforward, makes a lot of sense, right? Oh yeah, super intuitive. You could kind of guess that if you just thought about it for like 1 second. Yeah, so what you're really doing here is you're taking into account the fact that you have this del dot E. Okay, and that piece ends up in there, then you need to think about the fact that it's del dot E And these gradient operators sometimes have chain rules. So I have a del cross B with a cross B again, right? So you're gonna use all these operators in here and you're gonna expand them out, and there's some fun tricks in the book to help you do this. Maybe the great homework problem if you want. You want the homework problem? No, they don't care. Okay. This would be problem 816. Right, no, I'm kidding. All right. So why the hell would we do this? This is criminal, right? Gross. Yeah.
Is the first term, is that just from the row E? Or the row E add to all the three terms?
I forget how they're collected here, but you have this del EDT in here crossed with B that's giving you more terms as well. Because one of the things you have to keep in mind is that BDT is minus del cross X, sorry, del cross E. And so your del cross E's are gonna come in there from up there. That makes sense? Okay. All right. So we're gonna learn another fun thing today. You've seen this before. You love this thing from fluid dynamics. Tensor.
Why didn't we just do that then?
I'll show you, hold on. So to understand this BMS, which is awful, we have to learn a better version of writing. Then you're gonna see, oh, it's intuitive. Like right now, that doesn't make any sense to you. You might see some stuff that you're reminded of, right? Maybe you see one thing in here. What do you see in here that's popping out to you?
E cross B,
E cross B. That's a weird one, right? What is that?
it kind of like force.
Kind of like force.
What I was thinking, cause oh, that's B cross B, never mind.
Kind of looks like S.
Oh, yeah,
Kind of looks like the pointing vector. And what's the derivative of power? Energy. The derivative of power is respect to time. All right, you don't know that yet, but that's a force.
Oh, and isn't that work E squared?
This?
Well, yeah, the E squared reminds me of that.
Yeah, this reminds you of work too, right? Because this is like the energy stored in the E field. This is like the energy stored in the B field. It's like the gradient of those. Okay. But that? Okay, good. We don't know what that is. All right. So what's a tensor?
Give us
You've seen it before?
I just think back to an array.
Yeah, matrix.
That's exactly correct. I say the word tensor, you think the word array. In mathematics, we have things like vectors. What is a vector? If you're thinking computational. It's an array. What's a single variable? It's an array. Everything is array all the way down. What's the difference? Okay, let's just do an example really quickly. Give me a number. 2. That's an array of size 1. Give me 2 more numbers. 24. Nice. Beautiful symmetry. Okay, so let's look at that. So this is now an array of 3. Or I could think of them as a vector. Right? All right. One more number. Another number. 5. Very good. Okay, so this is what?
all of array.
It's still a,
Array.
and it's also a,
Column.
and it's also a, not yet.
Okay.
A vector. Vectors are one-dimensional lists of numbers. Now, the fact that it's like this is indicating to you that it's a column. You may not already know that. That's something that we're going to learn. If that one is a column, what is that one? a row. Make sense? Why it's a row? Alright, more numbers.
0.
Oh, 0, classic number. Wasn't a number till like 2,000, 3,000 years ago. Next.
Another 2
Huh?
zeros.
No, no. 2 zeros. The original. The original, please.
1.
1.
2.
Another classic number.
H bar.
What?
8.
8. Great number. Why is that a great number? Looks like snow. Oh, you got pocket snowmen in your hand. You're like, no one's gonna see this pair. Okay, what's this one? 10.
Yeah.
Hi. All right, there's 10. All right, what's that?
The matrix.
That is a matrix. Okay, matrix is rows and column vectors all put together for funsies. Okay, how do you indicate each one of these? Well, you can just say where they are. Right? Same way that we'll do on our computer. If we want to indicate where it is, you have to assign the location of a specific number. Okay, so I want to find the 0. How do I do that?
1, 1.
So that is 100% true when we're using a computer.
Yeah.
What's that?
I just said shit.
No.
It'd be 2, 2.
It's 2, 2 in real life.
2 more.
Because computers count from 0, but humans count from 1. First floor, second floor, third floor. Let's go to Europe. Bunch of weirdos. Okay. Start at 0. You're like, what? Gross. Okay. We're not in Europe, folks. All right. You may not have known that from the lack of free healthcare. Okay. So the way that we're thinking about this is that we have different components here. We can rewrite this one. We're gonna put a little map together. And this will be tensor XX. Next,
X1,
XY, correct?
XZ,
XZ. This one,
YX.
YX.
No, that one, no, that's.
Oh, this one's Z. Okay,
Yeah.
See,
ZX.
dy or
Y.
yeah.
Which one are we doing?
Alright, tell me where to go.
Go to the center one.
Center one, okay.
Y.
YY, okay, that's not confusing, right?
No, that's why.
YZ.
Where?
One to the right of our.
Okay, YZ. ZZ.
Yeah. dy.
Okay. So now we fully understand it, right? So IJ, T has components. Components. T, IJ, where I is which of these indices?
X.
X?
Oh,
Or
in
Yes.
row or column, it's one of the two.
it's the row.
You tell me.
It is.
It's the row.
It's the row.
Which row, right? So let's think about it, right?
Okay.
So this is column 1. This is column 2. This is column 3. This is row 1. This is row 2. This is row 3. Right, is that better?
Mhm.
So I tells you what?
Which
Which row?
Correct. And J?
That'd be fun.
You can read my handwriting, right? Okay. You may find that there are other ways to write this, for example, there are other coordinate systems. So you would do something, let's say we wanted to change all the X's to R's, thetas, and phi's. That would be your spherical coordinate system. You could still do that here. Okay. Tij has 9 components. Do you know what this one is? I know you're sick and tired of seeing these symbols. What's that? Okay, so we've heard of the delta Dirac function. Hopefully you did the homework, you saw it. And the delta Dirac function is going to tell us what?
Gonna give you the value right at 0.
Write it when the argument is 0. So delta Dirac has this fun property. You have something like this. Okay. Let's do okay. You see this in your day-to-day life. Like you're going to the grocery store, see this on the food aisle, where the location is of a specific food roll that you like. Okay, that's like how you tell where it is. So it's not on any other row except for right there. Okay, so which row is it on? 39. So when this argument is 0, you get what? All right. So that's how we use the Kronecker delta. Sorry, that's how we use the delta Dirac function. And we're going to use a new one. So in a tensor form, this is called the Kronecker delta. And we have another form that we'll use later when we start to do general relativity. I know, don't be upset. We'll do it later. We'll hint at it. It'll be cute. Okay. And this one here, we're just going to look at the indices. So just like the Dirac function over here tells us when it's 0 or 1 based on the argument, you're going to think of this as the argument. Okay. And this is going to tell us, this is a very specific type of matrix. Okay. And it's very fun. Okay, so what are the rules?
When row equals column, you get a value of 1.
Exactly. When I equals j, you get 1. Otherwise, you don't get anything. Okay? So another way of saying that is that the Kronecker delta just says when I equals j, you get 1. When I is not equal to j, you get 0. Okay? That's the identity matrix. Sometimes called okay, have you ever heard a mathematician or maybe in your quantum mechanics class, have you ever heard them call a number unity?
Yeah.
What does that mean?
It's like something with, is it with the adjunct? So it's like
dumbest number of all numbers. Yes.
okay.
So this is unity. Unit. No, it's a couple lines. And similarly, sometimes we just want to have fun names for stuff, you know, because we don't really get to be that creative as physicists. So we call this identity. No, there's a better reason for that, but that's what I'm giving you right now. Okay. Okay, so you've seen something similar to this tensor before. We saw it in a different class. What was that?
Fluid mechanics.
Fluid mechanics. Good. And what did we say about the different? What was the tensor reason?
Some are like rotational.
Okay, there's rotational and stress. Right? So like what this class calls stress. There's two types of stress. Types of stress are there. Right. Okay, so we said there's diagonal stress and off diagonal stress. And we interpret them physically as two different things. Shear and strain. Shear and strain. Shear is one of them. Yeah. Shear is what again?
Is that the
Right. So this is shear. Okay. Why is that? Because when I think about the directionality here, let's take this one. So let's take this is the force of y on x. Now, if they're not aligned, then force of y acting in the x direction, right, pulls it to the side. Right? As opposed to x on x, which would be same direction. So show me with your hands x on x. Right. X on x. And that is? Do it with your hands right now.
Oh.
Do it with your hands. Physically push. What do you feel? Force. Specifically?
Straight.
Try this and then try this. Which one
Oh,
hurts
okay,
more?
okay. This one.
Pressure.
Oh.
So x on x or y on y or z on z are pressures because they're in the direction of the force. Whereas when they're tangent to the force, they are pulling or shearing. So you have shears and you have pressures, right? Okay. So generally speaking, when we look at a stress tensor like this, we can deconvolve them. So I say the diagonal terms, okay? These are going to be your pressure terms. And these off diagonal terms are going to be your shear terms. See where I'm going? She looks at the hopefully out that door. Okay, let's go over here.
Not bringing the driver's mark, or the driver.
I didn't get a new one. I should have asked Maureen to buy one.
I'll ask you.
So here's how we think about this one. Okay. Diagonal terms have things like our minus e squared or minus e squared. Okay, that's these ones here. These are going to be our diagonal terms. And these are pressure terms. They're perpendicular to the surface. Our off diagonal terms are the shears. Okay. So let's see if we see any off diagonal. Let me put it together with the flux and we'll get back to it. Okay. I'm going to write that same equation here, F, little f. This is the force per unit volume. Okay, and I'm going to use this fun symbol. That's our Maxwell stress tensor. Okay. Minus okay. Let's see if we see all those terms. Yeah.
Wait, so that turns into that?
Yeah.
That's.
Isn't that beautiful? You don't like it?
I
Yeah.
just don't understand how it can mute that.
Where did the mu come from?
Is that in the?
That's an S.
Oh. Oh, yeah.
Pretty nice, right? Simple, right? Easy to understand. Super intuitive. So we saw this one already. We said, well, that looks like the pointing vector. And this is a time derivative of the pointing vector. And it was. We're so smart. We got the material so well. And this other stuff, right? This looks like b squared. These look like energies. In practice, they are derivatives of the energy. So these are going to be pressures. Okay? Not time derivatives, spatial derivatives. And then these ones are the ones that are a little tricky to understand. Okay. If we apply Gauss's law, okay, we can get the total volume instead of the volume per unit density. Okay, and we know that with Gauss's law, you can do some fun stuff. You turn our divergences into surface integrals, right? So we can say something like this. We like that? Okay. Minus epsilon naught mu naught ddt, and I'm allowed to take the ddt out here. Not just because I make the rules, but because you're allowed to do it. Oops. Break this. You may be upset about this last part. You've seen this last part before. What was pointing vector times an area? It was the power, right? But here it's the pointing vector times a volume. So we got to make sure that we keep that distinction in mind. Okay. All right. So if the flux of S is independent in time, then the total force only comes from the Maxwell stress tensor. Does that make sense?
Yeah.
Yeah, I'll say it 5 times probably. So this piece here, remember that the pointing vector takes energy in and out of the system, transported by the fields. Assume that that is equal in time. So what I mean by that is, let's take our box. The box is the room that we're all in, and the pointing vector would be any of us leaving or coming, right? So let's say we break people up. Tall people will be B fields, short people will be E fields, and we can measure going in and out, right? And we're just going to measure through the volume, right? We integrate this entire volume, how much S there is in the volume, and then see if it changes. So we count up all the people in the room, volume, right? Do all the fun E cross B, whatever we want to do. And then we wait 30 minutes and we count again, and we see, oh, nothing has changed. Okay. So that would mean that there's no contribution from the flux of S. So the pointing vector is doing no force. So that's what F is. Okay. And then the question is, well, what does this do? But what does this section mean again when we think about it in the context of like surfaces and garbage?
The surface vector, oh, T is.
Easy. Now you don't need to know the components. In fact, I'm going to not teach you the components because I don't want you to cry.
Is it like the stress is on like the outside of it?
Exactly. So we think about this in the context of fluid dynamics. We had it up here. We had these like forces due to pressures or stresses because we had viscosity. Here, we can think of this same object. Let's imagine the walls of this room. And let's imagine, some of us are moving around in this room and occasionally you bump into a wall. Bumping into a wall like this, moving that way in this X direction would be pressure. Be sliding along the wall like that would be shear. Right? Okay. So you just find out how many of them are hitting the surface of your box, add them all up good, and then that'll tell you the force on the box from the fields. Okay. There are ways to use stress tensors. I'm not going to show you the components right now, but I will show you some important rules. The first one is you have a vector. And you hit it with a tensor. Okay. And you just want a single component. What? Okay, that'll look like. Oh, maybe I can get rid of this. This is okay, though, right? You haven't seen what is on yet. Yeah. So this is just. That's a vector. Generally speaking, when we have vectors, vector notation, some people will just get rid of that sigma completely. And that will be what's called inferred. And so we saw this a little bit when we did fluid dynamics. Anytime you see repeated indices, let's say you have I and I, that means you sum over those indices. Okay, but I'm going to be very transparent about it here. So you might say something along the lines of AX T X X plus A Y T Y X A T T E X. This will be the X component. And so on and so forth. Right? fun one, right on your homework. I'm not gonna do it, Chris, but this is what it looks like. Okay. What?
Right?
Yeah, if you do the work. Right, if you can get it into the format where you have the tensors, and as long as you can write it ready to be put into, say, Mathematica. Or some other formalism that allows you to do tensor math without going through all the steps, fine, they're arrays, I don't give a shit. Right? But if you can't get it in this format, you don't know how to, then you're gonna learn it. It's the same thing with integrals. Set up the integral. Then look it up. Who gives a shit? Right? Integrals were solved hundreds of years ago. Okay? It's not like unique to be able to solve u substitution of an exponential. Okay. Another way to write this, let's say we want to write this one here. Uh-oh, this one sucks, right? So scary. What? The divergence of the tensor, right? So we have that.
Yeah.
So let's say you wanted to use f of y, like the force per unit volume in the direction x. You're like, well, I can never fucking do that. That seems awful. Well, this is how you would do it. We just have this sum del. You know, del has different components, right? And then you have t. And again, your I, since it's the repeated variable, this is the one you're doing the summing of. Okay.
Where'd you get the A from?
That's just a vector. I just chose some vector,
Just random.
a random vector A, to show how we do matrix math. Vector math, tensor math, whatever you want to call it. Okay. We want to see an example, how to use this shit?
Yeah.
Okay. I'm gonna need some board space, which means I need to reclaim some stuff. Let us imagine, very difficult problem. Okay. But we're gonna have a. We're gonna have a uniformly charged spinning sphere. Wow, such a good drawing this one. Right. What's that? He said it's a very good sphere. Thanks. Okay. So here we have a uniform charged spinning sphere. Let's say that it has some radius r, large r. Let's say that it has a rotation rate omega. Okay, and it has some surface charge, sigma. Okay. Okay. What is the force of magnetic attraction between the north and south hemispheres?
Oh, the omega was the surface charge?
Omega is the rotation.
Oh, sorry, not omega, sigma.
Sigma is the surface charge, yeah. Okay, so let's look at this problem for a little bit. Let's look at everything that's left on the board. Okay, we're gonna try and learn a little bit about how to use the Maxwell stress tensor. Now note that I did not give you the individual terms. So don't go on a rabbit hole right now. But instead, think about the different things that we'll need to know, similarly to how we solved these power problems from Tuesday, right? Think about what you need to know and how you would approach this problem. I'll give you 5 minutes to think about it on yourselves, and then start talking to your friends and see if they got anywhere. Okay? You can use the book, you can open the book if you need to look for a specific thing. Okay, how's it going? You wanna ask your friend, you see what they got? Sure.
That one I was doing, 'cause I was getting lost. Sometimes, right, it's great.
If it's not.
Oh, you're seeing it like something like this. So I was looking at, yeah. Yeah, honestly, I was focusing on like the stress tensor, or the tensor.
Yeah, the T part.
I think the DA is an art data format. Then my idea was that once we have the tensor, but we can figure it out, we can take any both pointer to R and like the integral of that. So you get like a top hemisphere. Like literally a bunch of circles. That, and then on the page you see the bottom. Literally, I don't know how to differentiate. Well, like,
You just add the most. Yeah. The other side.
I feel like the spin might have something to do with it.
Discovery.
And then we can do this, I think we can do this as like spherical. And then the spherical part is only really
But now.
the omega, they work in data. It's more like going around.
I mean, there's still.
And then find one that like bends down.
So there's still got the 14.
That's what it is.
This is so I think. Kind of. Yeah. Yeah, so I think we have to use the half a circle out and solve somehow. And then we mix it into the.
Wait.
I don't get how it.
Visible.
Like, I don't get how
The
it.
spin is only there. What if I only create something?
Oh, okay, well, I guess what it would do.
Alright, I have that. It is a problem.
All right, team, what do we got? Just completely lost. Okay, who is partially lost? Nice, all right, someone from the partially lost team. There's two terms here. Is our life solved by anything about, anything we know about these two terms?
There's nothing flowing around.
Or say that again, there's nothing flowing in or out.
Yeah, so the second term is plus time.
I thought you said that there wasn't changing time, that's why.
Yeah, I like that argument more. So we don't know necessarily that E cross D isn't non-zero. So I don't off the top of my head know the E fields or the B fields, but I do know that it's rotating at a constant velocity omega. So it's rotating at a constant velocity omega, then the DDT here has to be 0. Sick. All right, got one. Right? Okay. What? All right. So now the question is, well, I never told you what T was. So while you were all working, I started to write the T up there. Okay. And in particular, the thing that I would have asked you to try and find here is what are the E and B for a rotating sphere? Okay. Is that possible to know? Yes. Yes, it is possible to know. So in fact, if we look in our books, we'll find that example 511 does it for us. And it's just something we can find. So if you have a physical book, I would strongly encourage you, as you go through and you see an example of a charged cord or a ball with some amount of density inside of it, just mark them. You know, anytime you have an E that fits that configuration, oh, I know that that's in section 2.3. Or, point charge has this E and B, just write that down on a little piece of paper, and that can be your master document that says, here's where I found XYZ. Now, of course, if this is a homework problem, it'd be much easier, you just Google rotating sphere, E field, done, right? This type of derivation is important for you to know how to have done in ENM1, but now I'm gonna assume that you know how to do it. So you know Gauss's law, you know everything else. And so you can find the E field, right? Okay. Okay, so generally speaking, what will we need here? So you would have looked at this problem, you would have said the force of B attraction between the northern and southern hemispheres. So the first thing you did is you said, well, it's not changing in time. Okay, so first step one, no time variation. So this means that ddt of S equal to. Alright, everyone's internalized that. So the second step that you would do is you'd say, well, I would need what? Okay, I wrote the tensor secretly, but what would you need to find about the problem itself?
Oh, E field.
The electric field and the B fields, right? Okay. Find the E and B fields. Okay. So now this is where, teaching would come into play, and this is where I tell you that this piece and this piece do different things. So here is the Maxwell stress tensor. Okay. So this is the electric component. And this is the magnetic component. Okay. So what do they look like? They're right there. Okay. Didn't write the first term. You're all worried about that, huh? Yeah. Definitely. Okay, so what is this? When you delete the thing that everyone could see, all the numbers, we didn't even use it.
A certain row of E times certain column.
Yeah, so let's remember what this notation means again. This is Tij, this is gonna give me every component that I'm interested in. So whether it's XY, XX, ZZ, as I go through here, if I want a specific component, let's try this out, right? Let's try out, try it out for size. Give me two components.
230.
Not 1, 2, but let's do
XY.
XY, okay, thank you. All right. Not that I don't like that, but that's gonna get very confusing for me. 1, 2, 3, 4, right? Okay. All right, so this one is epsilon naught. Okay, so I's are now X's. What is this thing? Delta X line, the one that I just wrote. The Kronecker delta because it's an XY. It's what? It's 0. Good. I'm not even gonna write that second term. Plus. Good, and I'm gonna throw that other one out, right? The same reasons. So I can simplify this and I could say epsilon naught EX EY plus 1 over naught EX. Wow. Okay. So intellectually speaking, when we were talking about this weird tensor, we had all this shibbity shab, right? And we said this stuff was different than this stuff. and it was different than this stuff. Right?
Yeah.
So this was called the diagonal. And these were called the off diagonal terms. Okay, and what did the diagonal terms represent? Pressures. And what did the off diagonal terms represent? Shear. Good. So let's take a look at this here. Is TXY a pressure or a shear? A shear. Okay. All right. So this would be the component. This is the electrical shear. This is the tough, right? All right. Let's do one with repeated indices. XX. The first one.
Yeah. But in the A squared.
Yeah, that looks like it.
Yes.
Minus 1/2 EX squared. So now the Kronecker delta is 1. And I already got an EF squared, so this just gives me. And this one? Bada bing, bada boom. Right? So now I understand how to find these little tensor boys. And this is going to completely change how easy it is to do problems. To find forces with the fields is now simply finding the fields, E or B, whatever we want to know. Sometimes we need to know both. And then just pluggity chuggity and get all your components. You want the X, you want the component of the X direction? Okay, that's fine. Let's say you want F in the X direction. Well, first question you ask is, can I do this and grab the X component? Yes. Is this changing? Probably not. We throw that one away. We find the E's and the B's. We look at whether we want the magnetic or just the electric potential. Put those together, plug it all through T, and you'll end up with a formula for how the force works. Let's see this in practice, because you don't trust me. Okay, so I just want the magnetic component. And I'm going to tell you from equation, what is it? Example 511. I thought I'd go 11, but get it. B inside. Is 2/3 mu naught R omega in the z hat direction. And outside it's mu naught M over 4 pi R cubed. Two components here. 2 cosine theta R hat sine theta hat, where M is Sigma. That's not right. Super awful. No one likes it. Bad mistake. Okay. So before you write all of the components out, let's just be smart. Be super smart and clever and witty. Okay? Alright. Are there gonna be any R or theta directional forces?
You have it on the outside. Oh,
Yeah,
wait,
what?
wait. We only want the force of attraction between the north and south hemispheres. We're only really looking inside.
You tell me.
If we consider the inside, or we also, we want the outside as well.
Yeah, so if we think about it in the context, here's a sphere, right? It's fully charged. And I want to see the attraction between the north and southern hemispheres. Well, in order to do that, I really have to think about the force from one on the other. Right? The force of it on itself, not going to be as whole. Right? What about symmetry? Anything usual about the symmetry here? Spherical symmetry? Anything that breaks that spherical symmetry?
The disk,
The what?
the disk in the center.
Well,
It's not
Is there a
fixed
disc in
here.
the center? I mean, I drew it. That's just the hemisphere, top and bottom hemisphere.
Yeah, there's no physical disk.
It's a ball. Think about it like a basketball with charge and I'm spinning it off. I think. Imagine, of course.
I don't think spherical symmetry will work because of the pedal. Like even because there's no complete sphere.
That still seems spherically symmetric to me.
We can do that, but like, if we care so much about the hash, we can just do like, instead of phi is equal to pi for a whole sphere, we can do pi for the half sphere. So we
So
do
we
have
treat them like two different halves.
yeah,
halves.
we have half spherical symmetry.
Do we expect forces to change in this direction as in the field?
No.
No. Do we expect forces to change radially?
Yeah.
Maybe, we can't quite tell yet. Do we expect there to be a z component that matters here? Right, that's the strongest attraction. So we expect a strong north-south attraction. Right? Okay. So let's look at just the TDA component. Okay, so we want this thing here, T dotted in DA. And we want the Z piece. Oh, where to write this good? I'm gonna write it right. Not watching. Let's get the two. And then use those pieces over there. TZZ. And I just want the B one.
Squared.
What's that?
BZ squared.
BZ squared. Good.
Plus EZY. Oh, BZY. BZX.
Oh, wait. All the delta,
That's what happened. You need to square. Let's do that.
And the rest is. Okay, then I can simplify this. There's a BZ hanging out. I'm gonna collect those. And I'm gonna do something like B dotted into DA. That's fun. Now the question is what surface to integrate over? That's annoying.
done this in spherical, or
You can do cylindrical.
so,
That's perfectly fine here, right? So we think that there's some variation that we see that might not exist in R theta. Let's do Z. I like Z. Column. How do you, what surface do you want? I don't know, do you have a preferred surface? You like a circle? Okay, so where's the circle go?
we want to R.
Yeah, so let's make a little R theta plane, and then you said, let's slide it in between the two hemispheres. Right, slide it right on top, and then it's a closed surface, so I have to wrap it. Okay. So this is where we're gonna have some through here. And then through there, and that'll be our interval. Okay. Bada bing, bada boom, enter the room. Okay. All right, so this is as far as we can get right now. But we will come back to this and we'll do all the math, and math isn't beautiful, but it is straightforward. So it's just a matter of working through, grinding through the algebra. Okay? And then you can do a pretty complex problem, fairly straightforward. Any questions, comments, concerns?